Welcome to this video showing one of the features in Champ 3D, which is part of TICRA tools, and it can be applied to the design and analysis of passive, general multi-port waveguide components and complex feed change. We will design a typical waveguide component consisting of a rectangular to circular transition, followed by a circular waveguide with a 90-degree bend. We start a project from scratch, and we select the Feed and Waveguide tab. Any waveguide component, or device as they're called in Champ 3D, consists of at least one port. The square to circular transition has a circular port in one end and a rectangular one in the other. These ports can be defined by either pressing the New Port or by using the Create menu. We use New Port to create a standard WC94 port. We need to describe how the field at the ports shall be represented. In the case of WC94, it's logical to select circular coaxial waveguide port modal expansion. The number of modes should be chosen with care. If too few modes, the solution is inaccurate. If too many, calculation time will be too large. Convenient choice for this setup is, for azimuthal modes, Mmax equal to 3 and a minimum equal to 0, while for radial modes, Nmax should be set to 3. Manual convergence test is necessary. That is, after the scattering parameters are calculated, Mmax and Nmax should be increased, and it should be checked if the scattering parameters of interest will change. To demonstrate a different way of creating ports, we define the rectangular waveguide port, which is a standard WR90, by using the Create menu. In this case, we choose to define the port modal expansion through Waveguide Port Modal Expansion Settings, which could also have been used for the circular waveguide port. By specifying the number of unique cutoff frequencies, the expansion will include those modes with the 20 lowest unique cutoff frequencies. Now we've defined a circular as well as a rectangular port, and we're ready to create the waveguide device, the rectangular circular waveguide linear transition. Press New Device, Waveguide Devices, Simple Waveguide Sections, Linear Waveguide Transitions, Rectangular Circular Waveguide Linear Transition. First we specify the frequency range from 9 to 10 GHz in 3 steps. And then we specify the 2 ports of the device, WR90 and WC94. The analysis settings define the way the device is analyzed. All devices can be analyzed with the method of moment, MOM, and some can also be analyzed with mode matching. The present device, however, can only be analyzed with MOM, and we therefore press New to create a new MOM settings object. Here we choose the default settings, but remind you that for any MOM analysis, a convergence test should eventually be performed by changing the MOM settings repeatedly. Finally, we set the length of the transition to 6 centimeters, and we can now see the device details, and we can see the waveguide port coordinate systems, where the x-axis are indicated by red and the y by green. We now create the other device, the 90-degree bend, by selecting New Device, Waveguide Devices, Simple Waveguide Section, Waveguide Bends, Waveguide Radius Bend. We choose the same frequency setting as before. In order to subsequently connect it to the linear rectangular to circular transition, they have to have one port in common. Therefore, we select the already defined WC94 as one of the 2 ports, the one they have in common. The other end should have a port with the same dimension, but it would not be valid simply to select the same port as above. Instead, we can use a special option and create a replica of this port. We choose WC94 as the port to replicate, and we use exactly the same settings as before. The radius of curvature of the bend is set to 4 centimeters. The final step is to combine the two devices. We can do this in two ways, either from the Create menu or from the New Device tab. Let's select the Create menu, and we define the combined device as composed of the transition and the bend. To view it, we look for the device in the Device Explorer and double-click on it. Now that the combined device is created, we want to analyze the performance. Specifically, we want to see all scattering parameters. We select Add Command in the Commands tab and choose Export Scattering Matrix, which is the one that computes all scattering parameters. Here we do not need to specify a file name, but we may want to consider only those modes that will propagate at the specified frequencies, and therefore we select Propagating Modes here. All the modes specified in the port modal expansion settings are used in the calculation of the S matrix, but only the S parameters corresponding to propagating modes are exported to file. We run the job, and when it's finished, we can go to the Results tab and select to plot scattering parameters. In the data description, we can identify the input port excited by the TE10 mode as index 1. On the output port, we are primarily interested in the TE11 modes. There are two sets, set 1 being X polarized and set 2 being Y polarized. Since the input TE10 per definition is Y polarized, we look for the TE11 second set on the output with index 6. And to see the reflection coefficient and the interesting coupling from input to output, we should select input 1 to output 1 and input 1 to output 6 in the data selection matrix. You can use Control to make multiple selections. We then see the results shown here, where the wanted coupling is about -2 dB, while the reflection coefficient is better than -20 dB. These data are also exported to file in touchstone format. I hope this short presentation has given you a better idea of what you can do with Champ 3D, and I'll trust you will bring it to good use in your daily work. Thank you very much for listening.